Today, we are privileged to have invited Professor Cédric Villani here with us virtually to give the final plenary lecture for the 2022 edition of GYSS. He is most well known for his work around Landau damping, the Boltzmann equation, and optimal transport, for subsets of which he was awarded the EMS Prize in 2008, the Fermat Prize and the Henri Poincaré Prize in 2009, the much coveted Fields Medal in 2010, and many other awards. He is a well-respected author and have also received the Duke Prize from AMS. He wears many more hats beyond a mathematician and author, but I am personally most thankful for his extraordinary efforts in promoting mathematics and sharing his journey to the public, which I am sure have motivated many young scientists in their path to being mathematicians. Without further ado, let us now have Professor Villani share with us his mathematical career and achievements and his advice for budding young mathematicians. Professor Villani, please.
Hello, Singapore. Hello, GYSS. This is Cédric Villani speaking, here to deliver a plenary lecture about elements of my career, how I became a mathematician, my subject of study, my outreach activities, and things like this that I hope can be of any help or inspiration to the enthusiastic youth out there. I always loved math as far as I remember. As a child, always liking to concentrate on the shapes, on ordering things, on searching for things, on concentrating. And I learned math at school. My parents were teachers of literature, so it could not help me much about science. And my teachers were extremely helpful and influential, especially some of them when I was like 14, 15 years old. I remember them very vividly. But a large part I also read through books. I was an avid reader and always interested in books and knowing more with a lot of curiosity. Maybe mathematics was not my favorite subject. Maybe the subject which I most loved among all is evolutionary biology. Fantastic, amazing variety of shapes, behaviors, the dinosaurs and whatever, the evolution of the living beings and so on. I felt this was the most beautiful subject that there could ever be. Greatest show on earth, which by the way is the title of a song by my beloved rock band Nightwish, all about evolution of species. So this was my favorite subject probably, but in mathematics there also was something very special. Mathematics is not a science like any science. Mathematics is special because all the knowledge you need to have is within you. Everything is based on logical reasoning, and that's the only subject for which you don't have to trust necessarily the teacher when he or she is speaking. Maybe you are able as a teenager to spot a mistake in the reasoning of the teacher, and then the teacher has to admit the mistake normally. This happened to me a couple of times when I was a student in high school. My love for mathematics certainly comes very much from the fact that it's associated so much with inner life, with the possibility of thinking deep inside yourself. And it's something like an enigma, playing with the concepts, trying to find the right way to assemble them. Aristotle used to say that mathematics is the greatest form of beauty in the reasoning, and that beauty there manifests itself in the accuracy, in the ordering, in the commensurability, the relationships between the concepts and the numbers and the things. And I was very sensitive to this kind of aesthetics of the mathematical ingredients of a proof, how the elements can get together. Mathematics is the art of proof and reasoning. And if you love reasoning, normally you love mathematics, and if you love mathematics, you have to love reasoning. I remember vividly when I learned about what is a proof and what is it when you are putting up your reasoning. I was 12 years old, it was at school, and the teacher was explaining, now we are going to demonstrate things. I remember thinking, oh, this is interesting, and this was an important moment in my life. And somehow, in the coming 12 years after that, my progress in math was just every year learn to devise proofs more complicated, more sophisticated than the year before. More sophisticated arguments and more complicated reasonings, thinking for longer periods of time, etc. And after this period, when I was age 24, came what I believe is my first nice result, 1997, when by that time, as a researcher doing my PhD, after an encounter with Italian researcher Giuseppe Toscani, I was able, together with him, to find some good results, some nice results. Lower bound for the production of entropy in the model of the spatially homogeneous Boltzmann equation for a certain kind of interactions. Wow, what subject is that? When I was 12 years old, I was doing some, arguments of 10 lines, maybe proofs of 10 lines about simple geometric problems. By age 24, around the end of my PhD, I was making complicated papers of 50 pages, maybe more, with all kinds of reasonings and long formulas and whatever. And the subject was mathematical physics. Why did I go in mathematical physics? It was not my intention. When I entered École Normale Supérieure, a kind of elitist school for sciences and literature, when I entered École Normale Supérieure in mathematics in 1992, my favorite subject was algebra. But after a little bit of time, my favorite subject became analysis for some good and some bad reasons. One of the reasons why that through partial differential equations and dynamical systems, I hope to be able to do some mathematical biology and connect this with my lifetime love of biological beings like ecosystems, evolution, and so on. But didn't turn out to be the case. Following some advice by some of my professors, I went into the study of theory of gas, Boltzmann equation. I remember this is the first book which I read, the first book of research level, by the late Carlo Cercignani, one of the main experts of Boltzmann equation, who had read everything and written about everything about the Boltzmann equation. I would never have bet when I was in high school that I would go into mathematical physics. Boltzmann equation is the equation written down by Maxwell and Boltzmann in the 1860s, 1870s to describe the statistics of a huge collection of balls bumping into each other, gas from the atomic hypothesis. It was a fantastic subject in those days, very much daring. Who would have bet on these atoms in those days? And these guys were outstanding scientists, amazing. But when I was in high school, preparatory classes, I did not think highly of gas theory, thermodynamics. Subject looked boring to me. I never was in those days passionate about physics. And when I was in high school, by the way, my favorite field was geometry. However, I ended up going partial differential equations, going in the study of mathematical theory of gas, and I fell in love with it, literally. Discovered a subject full of beauty for the encounter between the statistical physics, probability theory, information theory with the entropy measuring the kind of disorder, information that there is in the statistical distribution of particles, but also fluid mechanics, applications in various fields of technology, and some amazing problems, big problems. Can you think that nobody currently has a good, sound, rigorous mathematical theory to explain phase transition in full rigor? Phase transition, like when water becomes too cool, it becomes like ice. When it becomes very hot, it will turn into vapor. Nobody has a full theory about this. These are familiar phenomena and still full of amazing mystery. And I went into this subject and really discovered enormous beauty. I was guided by my PhD advisor, Pierre-Louis Lyons, who received the Fields Medal in 1994 at about the time as I was starting my PhD with him. Also guided by my tutor at École Normale Supérieure, Yann Brenier, guided by later people whom I encountered, like Michel Ledoux, probably from Toulouse, Eric Carlen, mathematical physicist from Atlanta in those days. I always thought these four persons were like my four advisors, very much influential, so that I learned from them ideas and tools and techniques. They had different techniques and tools, and my style was a kind of synthesis between theirs. And so you see, it so happened that I was in this subject and I would never have predicted this. In life, you always have, I believe strongly this, to leave a good dose of chance in what will occur to you. And there it was eventually, my PhD thesis, defended in 1998, so I was almost 25 years old. PhD is certainly the most important diploma in science. It's not the highest one, it's not the first one, but it's the first one in which the advisor, in which the master gives you a problem that nobody knows if there is a solution. Even he or she does not know. And you go, so you really become a researcher, searching for a problem, fighting against the unknown when you are working on your PhD. And when you defend your PhD, you are the expert of that subject and you explain that research. And then you know if you're fit for research or if you will find another job, that there is something that there is absolutely no shame to have, of course. So I loved the research. It was a life that I would never have thought of. You know, I was a very shy kid with a lot of internal life. During the PhD, I started to travel like crazy, meet people by the hundreds in conferences, work on so many problems, and my life started to be so full of problems and problems and problems again, and I would love this. Publishing number of papers per year, having collaborators on various continents, not sleeping much, meeting and everybody and visiting dozens of countries, going from conference to conference, etc. Something which I really loved. Another thing which I loved and from the beginning was extremely keen on is about writing synthesis work, synthesis book. Even nowadays, in retrospect, when I look at my mathematical career, I think that maybe this is the activity for which I was most gifted. And I always was a teacher. Maybe this is in my blood. Always wanted to teach things which I just learned. This is my first significant book, Topics in Optimal Transportation. It grew up out of a course which I taught in Atlanta in 1999. You see, I had been in Atlanta because I was invited by Eric Carlen, who was part of my PhD jury. When I was there, I presented some result which I had obtained with some German colleague in some conference. In the presentation in Atlanta, there was a colleague from Benin who was extremely gifted, French speaking. We got along very well. So he invited me back in Atlanta to teach a course. He wanted a course on optimal transport, which was not my specialty, but which was related to my PhD subject and which I had done a little bit of work on. Optimal transport is the art of transporting matter from one initial configuration to another initial configuration, spending the least possible amount of energy. It's a subject that goes back to the 18th century, with developments, very important developments in the 20th century, and which had some extraordinary growth around the end of the 20th century, beginning of 21st century. That's the time when I was in Atlanta, 1999. Subject was burgeoning. I was not a specialist, but I was ready to take up the challenge. Learned, listened carefully, read so many papers and discussed with the experts and the specialists and taught the course, wrote notes from the course and wrote proofs, and the course eventually turned out to be this book, which even still nowadays, is very much used and kind of popular as a first book in the subject for PhD students, graduate students. So the best way to learn a subject is to teach it, that's for sure. And I became with that an expert on the subject and started to add this. So I was working on the Boltzmann equation, but also working in optimal transportation, going conferences about this, about there. Life became even more complicated. Books became more complicated. Here is another of my books on optimal transport. This one is almost 1,000 pages long. Took really some part of my life, I think 3 years of work, something like that. And when I read it, I think, gosh, how could I do this in only 3 years? The book received a prize, like a prize for a book which is particularly clear and particularly ambitious as a synthesis and so on. So it was also part of my life. Research life is searching, discussing, traveling, meeting, writing, teaching again, teaching your PhD students who become collaborators, teaching your graduate students, etc., etc. And I'm very French in my training. You know that mathematics is a very strong skill in France. And France is certainly the nation which has the highest number of the decorations and rewards in mathematics if you divide by the population, and second largest country in terms of number of fields medals in the world after US. So very much French, but also very much European, with collaborators in Italy, in Germany, in Spain, etc. But also with some important trips to the big American university campuses, in Atlanta, Berkeley, Princeton, each time for 6-month periods. I received number of offers. I, however, always believed it was important for me to go back to France and continue have my main activity there, teach there, and endorse some responsibilities. My most important work, maybe, or the one that gave rise to the Fields Medal, is the one on Landau damping, which is a particular damping mechanism, equilibration mechanism for plasmas. Think of plasma as a soup of electrons. And there are the electrons and there are the positive charges, but the electrons move much faster than the positive charges. So the dynamics of the electrons is dominating. And if you are near equilibrium and you perturb a little bit, would you expect that it would go back to equilibrium, to zero electric field? It's not obvious, because in plasma physics, the main equation, the Vlasov equation, does not have any friction, no collision, no irreversibility, no entropy increase. Friction is the main mechanism in our world for equilibration. That's fundamental in our world around us. Cars would not be able to stop without the friction, etc., etc. Friction is what also makes internal friction, the viscosity is what makes water go back to equilibrium after you agitate it or throw a stone in it. But in plasma there is no friction. And however, there is, under some circumstances, some assumptions, some conditions, there is equilibration. It's called the Landau damping, and in 2009, together with my former student and main collaborator at the time, Clément Mouot, we solved this problem. That is, we gave a mathematical proof based on this Vlasov equation, that if you take a plasma in equilibrium around a very smooth statistical distribution of electrons and perturb it just a little bit, then you will go back to equilibrium in a way that can be characterized and estimate the speed and so on. This was a work absolutely full of unknowns and long work. It's about 200 pages of proof, with some long proofs, with some new functional spaces, with some new techniques and so on. It's a work that lasted for 2.5 years, in which many people were met. In the acknowledgement at the beginning of the article, by the way, this is the list of all people that we thank for giving us some insights and some tools so that we were able to perform this work up to the end. We made so many mistakes along the way, it's like something like crazy, but eventually we believed and we managed to go through all these mistakes and correct them until the paper finally was published. Paper was decisive for getting the Fields Medal, and because it was solving an old problem, but also because it was giving some tools that would make it possible to solve some problems. You know, work has to have some posterity, some consequences, and the tools we used were developed, augmented by other people and by gifted researchers to solve some long-standing problems of stability of fluid mechanics and so on. So this is what eventually gave rise to that particular day, which I will remember all my life. It was 19 August 2010 when there was this big ceremony at the opening of the International Congress of Mathematicians, and I was receiving, along with 3 other mathematicians, the Fields Medal. Fields Medal is like a life-changing event. Puts you in the light. It gives you the opportunity to have visibility much beyond the borders of your community of scientists, so that you start to go on the radio, on the television programs, doing public lectures, teaching to kids, doing all kinds of interventions, etc. I not only was always interested in this synthesis, teaching, and so on, but also I had been trained in a culture in Lyon in which it was very important for us to communicate to the society and to do some outreach. And so I accepted many of the missions and challenges that my fellow Fields medalists had rather declined. I became president of association, I became director of institute, I started to organize some public debates, movie debates, I started to write books. This was the main success of my writing books, Birth of a Theorem or Living Theorem, a book which is about giving the reader the sense of adventure and unknown and human adventure that there is in the mathematical research. It was translated in 15 languages or so, including, of course, English, including Chinese, and a number, of course, of other languages, showing that in research there is the science, and when you want to talk about the science, you need to use some simple words to communicate to the outside world. But there is also the human adventure, the fact that there are emotions, dreams, ambitions, cooperation, fear, hope, etc., etc. And I wanted to convey all this that there is in the research life and why it is that it makes us so passionate about it. I went on recording some public lectures and a series of stand-up, quite some work, this stuff. I had to find a producer, I had to raise money, I had to write up the lectures. It's a set of 8 one-hour lectures and so on, intended for all kinds of audience. Quite some work, but also I wrote some comic books together with some drawers. I wrote the text for some artists. I made some dialogue books, etc., etc. Loving it and emphasizing the fact that mathematics is part of society with the applications, but also is part of the culture, part of the intellectual pride of making the ideas live. It's not just about solving problems and about finding some theorems with maybe some applications and techniques. It's also about being part of the culture and the pride of making ideas live. I even started to go in politics after that. This was 2010, just after the Fields Medal, starting to be in the militants for Federalist Europe. I am what is called a federalist, people who believe that Europe has to unite much more so that the nations be stronger and have a chance to continue influencing the course of the world. And it's something that for many years I stood up for, like before me mathematician Henri Cartan, convinced that also the European experience which I had lived through my training was very much representative of what we have to do for our youth. That Europe will be strong by the cooperation and travels and network between the youth. This eventually, after a long series of events, led me into national politics, French politics. I ended up being elected together with, being elected as a member of parliament at the time of when Emmanuel Macron was elected president of the Republic. I was very much seduced by the European line of the party of Emmanuel Macron. And once in parliament, started to do my best to make the interaction between science and politics in a time in which politics needs science more than ever. Because science is in the study of global warming, science is in ecology and the study of the living, science in the study of the health, in the study of technology, of energy making, and everything. I was in charge of a report on artificial intelligence, which became the basis of the strategy for France in artificial intelligence, doing a lot of lectures about this. Also in charge of a report about the teaching of mathematics to improve the quality of our teaching in France, which does have a lot of problems, even though we train some high-level researchers. We have problems with our students. And did a lot of adventures again, and encounters, and new files as a member of parliament. Reports about various subjects. Even ran for mayor of Paris. Was not successful, but it was quite an adventure. Here is the program which I had for Paris City. I'm very proud of the program even nowadays, even though, as I realized, the election was not at all about having the best program, but it was about a lot of other stuff. It was also a strong human experience with hundreds of people associated with that application, with that running for mayor. And it failed, but you never fail. It was, sentenced by Nelson Mandela. If I win, I win. If I lose, I learn. So this was also some good learning. And nowadays, still continuing to do my best, making the interaction between science and politics. I am the president of the French Scientific Parliamentary Office, which puts together members of parliament from the lower and upper chambers working on some scientific subjects with political content to help Parliament make decisions about subjects with strong science, like nuclear energy, diseases, vaccination, or quantum strategy, or neurotechnologies, or the future of antibiotics, or plastic pollution, or biodiversity collapse, etc., etc. Making also the best to put my experience at the service of political ecology. Nowadays, actually, for some good and some bad reasons, I got into some argument with my former party. I get out of the party. Now I'm part of the ecologists movement, of the environmentalists. Yesterday, I was on Twitch doing a special broadcast discussion with some experts about the collapse of insect biodiversity as part of the presidential campaign for the Greens, but also, as you see, as part of my efforts to make it that in politics, we don't just speak of the usual boring subjects, but we also speak of what really matters, the understanding of the world, the planet that we will leave to the future, and our way to go through the huge difficulties that our world and environment is going through today and how we can improve it, putting science and knowledge at the service of a better life, and still trying to do that in the future. As you can see, this is still to be continued. Thank you for listening. Please receive all my very best regards and encouragements for your future success. Bye-bye. Au revoir.
Due to time zone differences, Professor Villani will regrettably not be able to join us for questions and answers today. On behalf of Professor Villani and the organizing team, we thank you for your understanding and we hope that you had a fruitful and enjoyable time at GYSS 2022.